Hi everyone, my name is Gefen and I'm an undergraduate student at the Ido Kamener School. I study physics and electrical engineering here at the Technion. Today I want to present you our research about creating photonic CAT states and GKP states using modulated electrons. This project was done with Rafael, Alexei, Ron, Nicolas, and Ido, of course. So let's begin. When it's gonna. Okay, so let's start with motivation. This is not working, so we use this. Okay, so there are many ways to encode the quantum information on physical systems. The promise of optical platforms is that it enables you to create a room temperature, easily networked and scalable fault-tolerant quantum computer. To encode the information on optical qubit, you can use, for example, the polarization of photons. The promising ways today to do so is to use waveguides on chips. And to do it, you need to choose a way to, or discrete variable way or continuous variable way to encode the information. So in the discrete way, as PsiQuantum are doing, single photons carry the information on the dual rays, as you can see here. And in the continuous way, you use the infinite dimensional Hilbert space of photons to encode the information. And therefore, you encode one qubit over many photons. So this redundancy can be leveraged to encode, detect, and correct errors without destroying the encoded information. And in addition, you can even correct errors without using one photon's measurements. You can use a homodyne instead. Okay. So to do continuous variable encoding, which is what we're going to talk today, we need to choose the Bosonic code. So here are a few examples for Bosonic codes. For example, CAT codes presented at 1999 and GKP codes presented at 2001 by Gottesman, Kitaev, and Preskill.
But don't assume that everybody knows what are either of them.
Yes, I will explain now. Great question. So CAT codes are superposition. You can see here in the phase space, superposition of two or more coherent states. Okay, here we can see a four-legged CAT state. And GKP states are lattices of coherent states. Okay, we can see the Wigner function here. So if you're going to use it, you can create fault-tolerant quantum computer. Okay, and GKP codes are the most promised code and the most robust today. So let me just tell you a few more words about GKP codes. So this is the phase space. You can see here the GKP state in the phase space. And the GKP states are designed to protect against noise and optical losses, and you can build with it a scalable quantum computer. And it even enables universal photonic quantum computation without any additional non-Gaussian elements. But the big challenge today is to prepare this qubit, okay, to prepare this state. So there has been experimental demonstration how to prepare it in circuit QED and in trapped ion, but those are limited to the gigahertz range. And there are not experimental demonstration in the optical range. So this is still a puzzle. And this is what I want to talk with you about. We have a proposal how to create GKP states and CAT states in the optical regime. Okay, so what are we doing? Let's see the method. So first I want to explain to you background about the experimental method. To investigate the interaction between photons and electrons, we use the p-norm formalism. You can see here in the black plot the energy of the electron before the interaction, and in the red plot the energy of the electron after the interaction. In 2019, it was suggested to use the light in a quantum manner as well, and we can see here in this science paper that we're the first to show experimental aspects of it. So let me show you how we use this fundamental interaction between photons and electrons to do something else entirely. Okay? We want to explore the spontaneous emission of the electrons in the interaction. And we want to use the electrons to shape the light, okay? So in these papers, you can see that we show how to use it to create a Fock state, thermal state, coherent state, and even various entangled states. And the last paper, you will see the first quantum aspects of quantum light by free electrons, experimental demonstration. Okay, so what is our concept? So a few months ago, we have this moment on that we realized how to use free electrons to create useful quantum light states for quantum computers. Okay, so the concept is very easy. You shape the electrons, okay, into comb electron that I will present soon what is it. And then it interacts with photonic mode and radiates. After one interaction, it will radiate a cat state. And after more interaction with multiple electrons, it will radiate a GKP state. Okay, so let's see how it really works. So this is the scattering matrix of the PNM interaction. If we're going to take a comb electron, you can see here a few examples of comb electrons with different phases. The scattering matrix will be altered into a displacement operator. It means that if we're going to take a vacuum state, it will be altered after the interaction into coherent state. Okay? So if we're going to take a superposition of comb states with different opposite phases, the question is, are we going to get a superposition of coherent states with opposite phases, which is a cat state? Okay, so let's see what happens. We're taking this superposition of comb state. It's called comb even because the energies are even, okay, all the energies of the electron. And after the interaction, you can see here that the comb even is entangled to the even cat state, and the comb odd is entangled to the odd cat state. So if we're going to post-select the energy of the electron after the interaction, we're going to get a pure cat state. So this scheme is built out of three main blocks. The first one is the preparation stage, where we shape the electron to be a comb electron. Then the electron interacts with the photonic modes and radiates. And then we post-select the electron. So we can even generalize this trick to create higher order of cat states. For example, if you're going to take a comb electron with 4 h-bar omega between the peaks, as you can see here in figure D, we're going to get a cat state, a 4-legged cat state. Great. So now I want to take you one step forward to use it to create a GKP state. So what are we doing? We start with a vacuum state. And after multiple interactions with electrons, we alter this vacuum state into a squeeze vacuum state. Then we're going to change the laser phase and the distance with the electron to alter this squeeze vacuum state into a GKP state, while we assume that we post-select even energies at the end. So now you're probably asking yourself, what is the probability to post-select even energies every step? Okay, so this is the big surprise here. Apparently, it's very high. Because at the first step, the probability... okay, let's talk before this about something else really beautiful. Every interaction, the photonic states go through a convolution. So the photonic state will evolve according to Pascal triangle. And if we want to take it for a fault-tolerant quantum computer, we want to get a squeezing parameter above 10 dB. And you can see that we need to use 15 electrons to do so. So let's go back to the question about the probability. At the first interaction, the probability to post-select even is 50%, and then it's gonna go higher to 76, and then 84. And apparently that every step that we post-select even, the probability to post-select even again is higher and higher. And it will even converge into 100% when the state will converge into GKP state. So the two electrons interaction is a stabilizer on the GKP, and one interaction will act as an X gate. And you can see here that the probability to get for 15 electrons is 10%. And we can even increase this probability if we're going to start from squeeze vacuum state, and then we only need 3 electrons to get into the necessary squeezing parameter, and the probability is 30%. Okay, so for comparison, you can see that Xanadu's proposal is a 2% success, and I will not pronounce it good. Furusawa is 5% success. So let me just summarize. We show you how we can use the interaction between free electrons and light to create high-order catch states and to create GKP states with enough squeezing for fault-tolerant quantum computing. The key aspect here is the ability to shape the electron wave packet. And I just want to mention that this is a general concept. It can be implemented in other bosonic systems, for example, frequency comps and phonons. Okay? So that's it. Thank you for listening.